Welcome back. In the previous lecture, I described the challenge of cancer. Now I'm going to turn to links between cancer and the environment to try to identify causes, and hopefully once we know about causes, we can work toward eliminating those causes in the environment. The overall structure of this course was initially to talk about the challenge of cancer, and secondly, to do causes. Following this cause, I'll describe cancer as a disease, to review, then genes and viruses, cancer treatment, and screening. The idea of looking at causes is to look at population studies and see if we can relate a human activity, or something humans are exposed to, and the development of cancer. Two examples from 250 years ago in England tell us a lot about this science of relating cancer with something in the environment. In 1492, Christopher Columbus discovered tobacco. Well, he didn't really. Native peoples were using tobacco in the Americas long before Columbus came. But tobacco quickly became a major export crop from the colonies to Europe. And it was used for snuff. You know, you've seen photographs and pictures of people taking tobacco up the nose for snuff. In 1761, an amateur scientist, not a doctor, not a scientist, amateur scientist named John Hill, proposed in writing that oral cancer, cancer of the mouth as well as nasal cancer in the nose, were due to exposure to tobacco. 200 years ago, 200 years later, in 1964, the U.S. Surgeon General's report on smoking and health agreed with this conclusion. It took 200 years to get that into the cancer literature. Another example in England over 200 years ago. Surgeon Percival Pott was seeing a rise in scrotal cancers in chimney sweeps. Now, chimney sweeps were usually young boys, and they were lowered down chimneys, typically naked because any clothing might get caught in the rough brickwork of a chimney. And they'd be lowered down and they'd do their thing. And what was happening was that they were being exposed to soot, and there was more cancer of the scrotum in the folds of the scrotal sac. Percival Pott came up with a hypothesis, or proposal in science, that the soot exposure was related to scrotal cancer. And he convinced Parliament to pass a law that clothes, or tight-fitting clothes, or even a diaper, were mandatory on the chimney sweeps, and this lowered the incidence of cancer in chimney sweeps after that. Now we have to note what this was with Percival Pott. He found a specific cause, right, as something that was physical, like soot, not humors like Galen and other people had for 1,500 years that dominated cancer research. There was a physical cause of soot, and if he removed the cause or prevented it from getting into the scrotal sac, there was less cancer. This began the scientific study of disease in populations. And it continued in the next century, in the 19th century in England, with a gentleman named John Snow. Snow was the son of a coal miner who became a physician. In 1846, ether was used in the United States for the first time in operations as an anesthetic. Snow first used ether on the 7th of April 1853 on Queen Victoria for the birth of her son, Prince Leopold. And Snow, after that, became a very famous man. Everybody listened to what Snow had to say about medicine. At the time in the 19th century, one of the scourges of humanity, and it still remains a scourge in many places, was cholera. Cholera begins typically with a stomach ache and leads to vomiting and diarrhea, terrific loss of fluids, and if untreated, it will lead to death. In 1853, there was a cholera outbreak in London, and Snow lived in practice in the Soho area of London. At the time, most physicians thought that cholera was due to breathing in bad air. They called it miasma. And the bad air came from sewers. And if you just got away from the sewers and the bad air, you wouldn't get cholera. But Snow realized that it might be something else. The microscope had been invented, and when you put a drop of water under the microscope from a natural source, there are all sorts of living creatures, microbes we call them, in the water. And in dirty water, there were more microbes than there were in clean water. So Snow developed a hypothesis, an idea that he wanted proof of, and that was that cholera was caused by an organism of some sort, a living organism, that was in water that was contaminated by human feces. About 300,000 people in London got their water from two different companies. We'll call them Company A and Company B. Company A piped in its water from an inlet of the Thames River that was loaded with sewage. It was really dirty water. And people then just pumped it and would drink it. Company B, on the other hand, got piped in water from the Thames far away from where the sewage was. It was much cleaner water. What Snow did for science was that he counted cases. He was quantitative. He counted cases and he calculated the incidence of cholera in people who were drinking water from pump A and drinking water from pump B. And the ratio was 71 from pump A to 5 from pump B, a ratio of 14 to 1 from pump A where the dirty water was. Late in August of 1853, cholera was in Snow's neighborhood. And he found a pump that the people were drinking from the bad water, which is pump B. And he found a pump on Broad Street, which is a street near where he lived in England. And the pump was on Broad Street, and here are all the cases right near it. And so what Snow did was an experiment. He removed the handle to the pump. He just went out early one morning and he removed the handle. So people couldn't pump water from that pump anymore, couldn't get water that was, he thought, contaminated. And what happened was they had to get water from the other company, from Company B. The incidence of cholera was reduced. The new cases were reduced. The people who got cholera didn't fare any better, but new cases were reduced significantly. The key here is rigorous, quantitative science applied to human disease, in this case, a population. In 1854, a year later, a bacterium was isolated. Bacteria called Vibrio cholerae was isolated from bad water and later proven to be the agent that causes cholera. And you know, cholera is still with us. In 2010, there was an outbreak in Haiti after the disaster in Haiti. Thousands of people died from cholera, and the source may have been contaminated water upstream from where the people were drinking water, and the water had been contaminated possibly from UN soldiers at their camp. In this lecture and the following one, I'm going to talk about population studies and ask, what do they tell us about the causes of cancer? I'll start by defining the science of epidemiology and then describe how population studies can indicate what causes of cancer are. Then I'll describe how studies of individuals are done in epidemiology and how this type of evidence can be evaluated. In the next lecture, I'll take this evidence and I will tour the causes of cancer as described by epidemiology. Tobacco, diet, reproductive status in women, medications, pesticides, radiation, even personality. You have the idea that certain types of personality may be more prone to cancer. And finally, factors acting in combination. Well, let's start with epidemiology. What is epidemiology? Epidemiology is the study of the distribution and determination of states of health in a human population. It can be a large group of people living in a whole country. It could be people, if you want to do bad statistics, in a neighborhood, a small group of people. It can be people in a state, a city, whatever. The goals of epidemiology are the prevention, surveillance, that is, where is it, and control of health disorders in the population. In the United States, epidemiology is largely a function of an organization called the Centers of Disease Control and Prevention, and they put out a weekly digest you can read online called MMWR, Morbidity and Mortality Weekly Report. The aims of epidemiology are several. First of all, epidemiology assumes that human disease may be related to the environment. That's what they're getting at. And you can do natural experiments, things that happen by accident. So something like correlating cholera cases to a contaminated water. So that's a natural experiment. People were drinking bad water and they got cholera. And then you can do human experiments, right? You can do human experiments to cement this relationship like Snow did by removing the handle on the pump. So people couldn't get the contaminated water and the cases went down. The ultimate aims of epidemiology are to establish a cause and effect relationship. This is hard to do. I cannot emphasize that too much. Because the challenge is that most diseases have a triad, three different aspects to get the disease. The agent, the thing that might cause the disease, and that could be inside the body or something on the outside. The host, what's the condition of the person, and the environment. So let's look at the flu, for example, influenza. The influenza agent, well, we kind of know what that is. It's either a virus or in some cases a bacteria. The host, well, if I'm exposed to the virus that causes typical flu, my immune system may fight it down. I actually have the vaccine this year, so my immune system may fight it and yours may not because you didn't get the vaccine. Or you or I may be immunocompromised for some other reason. Our immune system isn't working well. There may be genes that different ones of us have that make us susceptible or less susceptible. You'll see this with cancer later. And the environment. Right? If you're not going to catch the flu if you live in a farmhouse in the middle of Iowa where your nearest neighbor is 20 miles away and you don't interact with them very much. On the other hand, crowding, malnutrition and stuff spread the disease. So agent, host, and the environment. How do we get information for epidemiology? What are the sources of data? For cancer, one of the best sources of data might be death certificates, right? What's the cause of death? Lung cancer, colon cancer, etc. And generally in a death certificate by law, there are demographic data. There are data about the person, what their job was, that is on a death certificate as well, how old they were, where they lived, spouse information, etc. And they'll put in primary and secondary causes of death. The problem is the accuracy, that the physician has to be accurate in what she or he is putting down on the death certificate. For example, in the 1940s, if a person had multiple diseases and died, and diabetes was one of them, diabetes went to the top as the cause of death, even if they may have died of something else. So death certificates you might think are good, but they're not as good as they could be. Now, of course, then there are population-based data on cancer incidence. Cancer, where I live in Los Angeles, California, is a reportable disease. What do we mean by that? When a physician makes a diagnosis of cancer, they have to report the disease to a public health agency, to a central agency that then puts it into a database. That's what a reportable disease is. There is a huge cancer reportable disease database called SCER, Surveillance, Epidemiology, End Result, SCER. It's run by the National Cancer Institute in America and by the CDC. Since 1973, in a number of regions of the country, cancer has been a reportable disease. So they know all the cases of cancer. The database has several million cases now and well over 100,000 new cases every year. It's a huge database. And this database, covering about 30% of the population, is representative. For example, there are, if you look on the map, rural states like Alaska. There is states with a high American Indian, for example, New Mexico, Arizona. There is an urban area like Los Angeles, San Francisco Bay Area. There's places with people on farms in Iowa, for example. There's counties in rural Georgia that have a large number of African Americans. It reflects overall the population. And in SCER, they record every time there's a cancer case diagnosed, the age, the sex, the race, the occupation, the family, the incidence, what the type of cancer is, the death of cancer, and the therapy. So there's a huge database. And so if you want to know how many people got breast cancer who live in a certain location near a farm or something like this, and you can find out using that database. So we can get a lot of information from this. A second source of information that's pretty good now is the EPIC study, the European Prospective Investigation into Cancer and Nutrition. The EPIC study has been going on since the early 1990s, about 20 years old, and it's enrolled about 500,000 people from all over Europe in the countries that are shown in the map. This is studying diet and other habits that people have, as well as cancer. It's a prospective study because these people don't necessarily have cancer yet. They're going to be followed for a long period of time, and blood samples are taken periodically and stored to get information on that in case people want to know what chemicals the people have in their body as represented by blood. A third example to give information on cancer is what's called the Nurses' Health Study, started in the United States, started in 1976, long time ago. It's a prospective study, again, following people over time. Nurses from 11 of the most populous states are being followed. There's over 100,000 nurses have questionnaires they're filling out every 2 to 4 years on their health, on their diet, on diseases they have. And they take blood samples every 2 years as well. So again, a huge amounts of information. Before we proceed with epidemiology data, we have to look at the language of epidemiology and differentiate between some of the aspects of that language. First, a causative risk factor. A causative risk factor is the actual cause of the disease. If you take it away, the rate goes down. For example, smoking and lung cancer. That's easy. Another one would be a descriptive risk factor. A descriptive risk factor distinguishes people who are at increased risk, but is not the actual cause. For example, Caucasians with light skin have an increased risk of sun-caused melanoma, lethal skin cancer, versus dark-skinned people who have pigment that protects them against the damaging rays of the sun. Risk is the individual's chance of getting disease, and you always have to keep that in mind, that the risk for cancer might be quite low, even though it's reasonably high lifetime, but in an individual case it might be quite low. Relative risk is the number of times higher the risk is of getting the disease in those who have the same risk factor as compared to those without the factor. For example, Snow, remember, he counted the ratio of cases in the people who were exposed to bad water and unexposed to bad water, right? And he got a ratio of 14.2 to 1. So now that we've put away the idea of what epidemiology is, I want to begin by studying what epidemiology does and what it finds in studies of populations indicating cancer causes. One way we can do this is looking at international comparisons. So, for example, we showed this in the last lecture. Here are some cancers at different higher and low rates from different parts of the world. For example, esophageal cancer is highest in Kazakhstan, has been reported, versus Holland by a ratio of 200 to 1. Why would that be so? Right? So we really don't know. It could be heredity. People live in the Kazakhs may be different in their genes, or it could be environment, right? It could be something they're exposed to. One way to unravel these is to do an immigrant study. That is to watch what happens when people in one area move to another. An area that has a certain rate of cancer, move to an area that has a different rate. Will the rate change over time? Because genes don't change over time. It takes many, many generations to see significant genetic change in populations of humans. Here's a study of cancer in Japanese immigrants to the United States. And it's a study of stomach, colon, and liver cancer. Let's just look at stomach cancer. In Japan, stomach cancer is pretty high. Incidence of 8.4 per 100,000 relative to Caucasians is 1.0. So in California, so that's 8 times the rate of Caucasians in California. First generation in California, whoa, down to 3.8. Second generation, down to 2.8. And another generation, it'll be down to 1, which is the same rate as the Caucasian Californians. Colon cancer, less in Japan, only 1/5 the rate in the United States in Caucasians, and goes up in a couple of generations. And you can do this for a number of other cancers. Now look, the genes are not changing in these people, not significantly to the extent that it would cause a change in cancer incidence. So it's obviously something in the environment. And when you do careful studies to look at the environment, very often you come up with diet as a major factor. We'll talk about that later. In addition to doing these immigrant studies, looking at a population going from place to place, we can have a population that's in the same place being exposed to something new. And now I'm going to describe as an example of these kinds of studies, endometrial cancer, which is a cancer of the endometrium, which lines the uterus in women. This is called descriptive epidemiology. In the 1960s, late 60s and early 70s, there was a fascinating increase, disturbing as well, in endometrial cancer in parts of the United States. So there's the incidence per 100,000, and here are different regions. In San Francisco Bay, it went up quite a bit. In Honolulu, Hawaii, went up quite a bit. On the other hand, in rural Connecticut and rural New Mexico, didn't go up much between the years 1970 and 1976. This is called descriptive epidemiology. We're just describing something that happened. The disease went up, right? When you look at who the women were, in an overall population basis, the women in the San Francisco Bay and Honolulu areas are more affluent. The women in the rural areas are less affluent. So now scientists ask, well, what were the affluent women doing that was different around that period of time? And what they were doing was changing their exposure to estrogen. In the 1960s, menopause, a disease, it's not a disease, became a disease. Menopause is a time of life where women stop ovarian cycling, and their estrogen levels go down. And so doctors came up with the idea, well, if you don't want all those symptoms, let's medicalize it and turn it into a disease and say, well, we'll give you postmenopausal estrogens. If you look at spending on postmenopausal estrogens around the time just before this increase happened of endometrial cancer, you see that there was a great increase in spending on estrogen sales, followed several years later by an increase in endometrial cancer. So this is correlational, right? This is relating one thing to another. In this case, we're speculating that it's the estrogen that caused the endometrial cancer. Now, what does estrogen do? It prevents heart and bone problems. It's a good use in the 1960s, but it may have promoted some cancers as well. Is it a reasonable correlation to make? Of course it is, because estrogen does affect endometrial cells. It does land on them and do things to the cells. But when we look at data like this, estrogen sales and endometrial cancer, we can come to a tentative conclusion, but we can relate the two, but we can't prove it. And the reason we can't prove it is we cannot tell whether the women in this population who got endometrial cancer are the ones who bought postmenopausal estrogen. We just know in the overall population that sales went up. To do this, we have to do studies on individuals. There are two types of studies on individuals for cancer causes. They are case control studies and cohort studies. In a case control study, we take cases who have the disease and controls who don't. In this case, endometrial cancer versus not endometrial cancer. And then we ask each one of them, were you exposed to estrogens or not? Were you exposed to estrogens or not? So this graphic shows you the cases will be A, the controls will be B, and the exposed or not exposed, C and D. And you see this, the odds of exposure in the cases is A over C, which is the cases exposed versus not exposed, and the odds of control, so here's the exposed versus not exposed. And in the controls, B, which is the people who were exposed, and D, who were not exposed to the postmenopausal estrogens. And you can make a calculation. Well, here's some real data. This is from a single medical practice. There were 205 cases and 205 controls. And of the cases, 32 had been exposed to postmenopausal estrogen, and only 12 of the controls. And we do the mathematics, you ended up with a relative risk for exposure and endometrial cancer of 3.0. That's a case control study. A cohort study is different. It's the obverse. Here, you start off with two groups. One group has been exposed to the risk factor. The other hasn't been exposed to the risk factor. Then you ask the question, okay, you people who are exposed to the risk factor, get cancer or not? You people not exposed, get cancer or not? You see the difference between that and a case control, I hope. So here it is. People with the exposed and not exposed are the primary groups. And then we ask the question, do they have the disease or do they not have the disease? And that's the control, and you do a calculation that you end up with a relative risk calculation as well in a cohort study. Well, here it is for estrogens and endometrial cancer. Women with and without exposure for 10 years to postmenopausal estrogens were evaluated for endometrial cancer. And you see there's about 1,000 women in each group. Exposed, 1,000 women, that's in green. Not exposed is in orange. And you see 35 of them got the disease, whereas the not exposed one, only 11 got the disease, and you end up with a ratio of 3.4, which is pretty similar to the 3.0 that we just saw. So these are case control and cohort, the two ways of doing epidemiology. The problem with epidemiology is that you need to evaluate the evidence. There are many, many small studies out there showing small relative risks. Typically less than 3, right? A relative risk of 2, etc. Supposing your risk of getting a certain type of cancer is 1 in 1,000, and that's pretty high for some cancers. Now it's going up to 2 in 1,000. It's very hard to measure that reliably. And you end up with conflicting data. You look at a daily newspaper or online and you'll see such and such and such and such related to cancer. You have to ask, what's the relative risk number? This has led to what a great physician once called an epidemic of anxiety. Everybody's worried about things that are going to cause cancer. Now, two challenges limit epidemiological studies, two major challenges. And those two challenges are confounding variables and bias in study design. What's a confounding variable? A confounding variable is something that's hidden in the population study. You're not aware that people are doing it. For example, cigarette smoking. A lot of people smoke, and this confounds studies, or past smoking. For example, there was a case control study on coffee drinking and pancreatic cancer that got headlines some time ago. Had a relative risk of twofold risk of getting pancreatic cancer if you were a coffee drinker. They corrected in the two groups, the cases and controls, for smoking. They both had equal number of smokers, but they did not interview about past smoking. So they said, in other words, okay, so they weren't correlated. And when you corrected for people who had smoked in the past, the relative risk went down to 1. So our conclusion was not valid because of this confounding variable. Another confounding variable is bias in study design. What do I mean by bias in study design? You've got to choose the right controls. Think about this. We're doing a case control study on, for example, electromagnetic fields, exposure to high-tension wires, and the fields of electromagnet that come from high-tension wires, and childhood leukemia. This was actually done, and brain cancer. And they found that children who were living near these wires got more brain cancer and leukemia. It was a sensational discovery, by the way. But how did they get their controls? They knew the cases. That was people in the medical practice. How did they get their controls? They did it by what's called random digit dialing. They took the phone number of the cases and they randomly changed the last 4 digits. You know, the prefix was the same, so it's the same general area. And then they randomly changed. So 5551234 might be the actual phone number of the case, and then the control, they would start at 5551342, 5551423, et cetera, et cetera. But let's think about this. Poor people are less likely to be home during the day to answer the phone, even if they don't have a cell phone. They're less likely to volunteer to take part in the study. They're less likely to call the researchers back. So there was a bias to rich people in the control group, right, and poor people. And so it turned out that the study of electromagnetic field, the people they got in touch with to be the controls, were richer. And so the study showed that there was a correlation not only with living near high-tension wires, but with breastfeeding, with maternal smoking, with traffic density, lots of things that were markers for poverty. So the controls were richer, and now saying that they're equal and the only difference between the cases and controls was being near a power line is going to be problematic. Evaluating epidemiology evidence has to be done, and there are 6 ways that I have to evaluate them. First, are results of different designs of the investigations consistent? Do case control studies and cohort studies give the same relative risk? Second, have different studies using the same design given the same result? That is, case control study in one place and another place give the same result. Third, are the relative risks large? Not 1.1 or 10% more, but 300% more or 500% more. Fourth, is the agent, the suspected thing that causes cancer, specific for one type of cancer? Because different cancers are susceptible to different agents. Fifth, is there a dose-response relationship? That is, in these epidemiology studies, if you're exposed to 1 unit versus 10 units, you should get more cancer, right? 10-fold more cancer than you are if you're just exposed to 1 unit of the agent. And sixth, is it biologically reasonable? Estrogens, right? Is it biologically reasonable that they might be related to endometrial cancer? Well, here is the evidence for evaluating estrogens and endometrial cancer. First, are the results of the case control and cohort studies consistent? Absolutely yes. For the case control I showed you, the relative risk was about 3, and for the cohort studies, the relative risk was about 3. They're consistent. Second, do different studies of the same design give similar results? Yes. Okay, they gave consistent between 2 and 4. Is the relative risk large? Yes. In fact, the relative risk goes up to 10, right? Sometimes in some of these studies. Fourth, is it specific for a certain type of cancer? Yes. We were looking at endometrial cancer, but in addition, breast cancer. Fifth, is there a dose-response relationship? Absolutely. In the short term, the relative risk was about 2 to 3, and in the long term, it was between 8 and 20. The longer you were exposed, the more the problem. And sixth, is it biologically reasonable? Absolutely yes. There is a receptor protein, there's a molecule inside endometrial cells and in breast cells for estrogen that is not present in other tissues. So in this lecture, I've introduced epidemiology. I've described what it is, how it can be done on populations, and how it can be done on individuals, case control and cohort studies. And finally, how we evaluate these epidemiologic experiments. In the next lecture, I'll turn to the results of these studies. Thank you.